Well, here we go. I'll start, I guess, with the quiz right quick here. Let's see here. See if this lighting will be okay. It should be okay. I don't have the best lighting down here, but it'll have to do. All right, so quiz 2, I had 20 questions, well, 19 questions, I guess. And let us just kind of work our way through here right quick. I'll try to be quick. You can pause and scribble stuff down if you need to. First of all, we're supposed to find an orthonormal basis for this set right here. For the basis for the perp. Now the perp is a subspace, right? And then we're supposed to find the point in the perp closest to 1, 2, 3, 4. So first of all, to find a basis for the perp, we just find the null space of the transpose. Is just basically lay these column vectors flat like row vectors, do the row reduction to get to that. And then, that means x is equal to x1 minus x4 is equal to 0, so x1 is equal to x4, and likewise this equation here gives me x2 is minus x3 minus x4. This should be familiar. This is the null space basis calculation again, right? And so that gives us this, which we can factor out the x4 and x3, gives me this and that vector. Well, that's a basis for the perp, but it's not what we want. It's not orthonormal. So what we do, we Gram-Schmidt this thing. So to start with, keep that one, call it u1 prime, and then u2 prime, which I've been calling v2 prime this semester, but it's just a label, whatever. We take the vector, take the second vector, this one, right, and subtract the dot product of the first with the second divided by the, the dot product of the first one with itself, which is 2. And that should give me the resulting u2 prime vector, which is this. And then, you don't want fractions, so pull a half out. That gives us 2 minus 1 minus 1, 2. Excuse me. And then as a quick check, that is perpendicular to that, right? Because I get the dot product of u1 prime and u2 prime is in fact 0. Good check. And then we normalize those. So divide by the square root of 2, and over here, ignore the half. 4 plus 1 is 6, plus 4 is 10, so divide by square root of 10. That's a unit vector. So there is your orthonormal basis for the perp. And then to calculate the projection, you simply take the dot product to select the component in that direction, and then multiply by the vector to give it that direction. And since u1 and u2 are an orthonormal basis for S perp, this gives me the projection onto the perp, which gives me this and that, which works out to that. There you go. That is the closest vector to the perp in problem 1. Now, as I mentioned to you guys in class, this first 7 problems in this quiz were previous test 3 questions in Math 221, I think in the spring of 2024. Now here we have the span of these 3 4-dimensional vectors. Notice, as I say here, that, now this one's a little bit tricky, so watch out for this. The starting point for Gram-Schmidt is linearly independent set. If you try to do Gram-Schmidt on a linearly dependent set, bad things happen. So maybe you guys ran into that when you're trying to work this problem out. I don't know. So first things first is replace this with a linearly independent set. And that's easy enough to do, see, because the third one is the sum of the first 2. So if I just do Gram-Schmidt on the first 2, that will suffice. And so I do that. We get to this lovely basis down here. There you go. That's my orthonormal basis for W. The perp to W, I again take a basis for W, which is V1 and V2, transpose that thing, reduce, null space basis. This time, as I say, sweet, these are already orthogonal. We don't have the Gram-Schmidt this time. Hooray! That doesn't always happen, obviously. And so there's your basis for the perp to W. And then to calculate the projection onto W, I use the basis for W back up here, right, and took the dot product with U1 and U2, and that gave me this, which then gave me all this jazz, which then after, as you can see, I made a mistake. Anyway, after some suffering, I got that formula. Yay! All right. Obviously, if I put one on the test, I would try to make the formula work out a little bit easier, because nobody wants to grade that. All right. Now here's the quadratic form problem. Here's the formula. From this we can extract the matrix. We always take half of the cross terms, make this matrix symmetric, because then the real spectral theorem applies. Woohoo! And so the matrix is 1, 3, 3, 9. Great. The characteristic equation, and let me slow down here because this you must do carefully. There's one thing that matters doing carefully on a linear algebra test. It is calculating the characteristic equation because it characterizes the eigenvalues, and if you get those wrong, everything else you do is, well, kind of garbage. So, sorry, but it's just the way the cookie crumbles, and sorry, but it is what it is. Anyway, so this one here, notice that the determinant of this matrix is actually 0, because 9 minus 9 is 0. So this is a determinant 0 matrix, which means it's not invertible. Fun fact, if the matrix is not invertible, that means that the null space is non-trivial, which means that there's at least one non-zero eigenvector with eigenvalue 0. So look for that. If the determinant of your matrix is 0, you can expect that lambda should factor out of the characteristic equation as it did here. Not an accident. So eigenvalue 0, eigenvalue 10. So I write down a minus 0, I got that. I tilt my head and I squint. Oh, I just say, okay, u plus 3v, so u is minus 3v. And I choose, v equals to 1 and u equals to minus 3, and then I normalized it by dividing by root 10. Plug in the 10, work out the eigenvector. That ends up giving me this vector here. These will be perpendicular. If they're eigenvalues of if these are eigenvectors of distinct eigenvalues for a symmetric matrix, they will be perpendicular. You can look for that as well if you want, but you don't have to. And then for part C, we're supposed to write the formula in the eigencoordinates. And, well, actually, I forgot what the actual instructions were here. Uno momento. Express x1 and x2 as functions of eigencoordinates. y1, y2, show how the formula simplifies. Yeah, so that's what I did here. Eigencoordinates y, which gives me this. Now I've been using x bar and y bar this semester, but sometimes I contrast x for the regular coordinates and y for the eigencoordinates, like, whatever. There's different notations you could use. But switching from x to y as I did here, we go from this formula to just 10y 2 squared, which is kind of neat and kind of the point, actually. So remark, generically speaking, if we have a symmetric matrix and we write the quadratic form like such, if we have eigenvalues 1 through n, lambda 1 through lambda n, and beta is an orthonormal eigenbasis for A, then if we introduce eigencoordinates like this, then we have this formula, this calculation. I did this calculation in class as well, I believe. So replace x with the eigencoordinate y. What happened there? That was supposed to, oh, there it is. That is y transpose. And this is diagonalizing A, so lo and behold, there you go. So this is general thing to look for. We can diagonalize the formula for the quadratic form by using the orthonormal eigenbasis. And that's always available to us if the matrix is symmetric. That's the real spectral theorem. This here, you're supposed to decide max, min, or neither, given that this is the quadratic form. So yeah, that's the matrix, and lo and behold, the eigenvalues are -2, 4, and -2. -2 apparently was repeated, and yeah, so that means the formula then in eigencoordinates is like -2x bar squared, -2y bar squared, plus 4z bar squared. That means that it's neither a max nor a min, because when you have a mix of positive and negative eigenvalues, that means you can increase in one direction but decrease in another as you're close to the the point of expansion. Now, this one is a little fussy. Let's see here. I don't have the details for the Gram-Schmidt on this one, but if you Gram-Schmidt, you get to this, and that means that my Q matrix, which is formed by the orthonormal basis for a column space. So I basically just orthonormalize the columns, assuming the columns are linearly independent, I suppose, because otherwise I can't Gram-Schmidt, right? So in any event, oh, it's about to get loud here. The kids are home. So that brings me to A is equal to QR. So I can solve for R by multiplying both sides by Q transpose. That's how we find the R in the QR decomposition. And lo and behold, there's the QR decomposition. As I mentioned down here, it helps with the least square solution. If you put, A is equal to QR, then it's nice in that you get this Q transpose Q, which simplifies down to R trans, that's the identity, I believe. And so that just simplifies down to like, what am I doing there? Oh, that's not this to that. This simplifies R down R transpose R X equal to QR transpose B. And okay, fine, getting to the point as I say here, that gives us R transpose RX is equal to R transpose Q transpose B, which is, since R transpose is invertible, because that's the nature of the R, then that gives us, we can just solve Rx equals to Q transpose B, which is actually an easier equation to solve. So there is an application of the QR decomposition to least squares, and I think that's what I'm working through here. All right. So anyway, we move on here. That's problem 5. Best fit line, standard test question, right? You write down the equation of a line, plug in the data. This gives us 3 equations and 2 unknowns, which is inconsistent as it happens. And then to find the best approximation, we multiply by the transpose of the coefficient matrix. That gets us to these normal equations right here, right? And then, of course, this time, that's that. And so then I can solve for C. I can use multiplication by inverse matrix for these little 2x2 systems. That's what I usually do. And there you go. That's the least squares line right there. Oakley dokley. That is problem 6. Problem 6. So still, this is all test questions. Although I think I wonder about that QR one. Maybe that was, well, anyway. Maybe I was meaner that semester. Let's see here. So, I have a QR decomposition with 2 columns, and I think that almost accomplishes the same. If you understand that problem, you understand one with three columns. And anyway, I don't know if I need to. The sophistication of the QR decomposition in the previous problem is like a little bit more than I want. Maybe, I don't know. I've forgotten what the problem was. All right, so the problem here is you're given this matrix. You're supposed to diagonalize A and then calculate the matrix exponential. Oh, this was unpleasant. So diagonalizing A is easy enough. I feel like this might have been a take-home test or something, guys. Some of this is like, this was definitely a take-home test, right? Yeah, this was definitely a take-home test. So, it was true. It was the first 7 problems in a test, but I think it escaped me that this was a take-home test. Now it's duh. So sorry, I seem to have given you take-home test problems in your in-class quiz. But hey, you were working together, so it made it okay. Anyway, yeah. So I got these eigenvectors, right? And lo and behold, these are the eigenvectors for A. And I think probably could work that out if I was less lazy. Here we could calculate the characteristic equation, factor it, like so, and then you can find the 3 eigenvectors. Simple enough. But anyway, details aside, I do have other details to show you. That gives us this eigenbasis, and then we can make the matrix, and then if we do beta inverse A beta like that, that diagonalizes A. Now here A is not, notice this one is not symmetric. See that? It's not symmetric. And so, in fact, this eigenbasis is not orthonormal, and like this eigenbasis here is not, sorry, I can't see that. Yeah, this is not orthonormal, so to actually calculate the inverse, you really got to calculate the inverse. Oh, and so, yeah. But anyway, yeah, I had assumed P inverse was P transpose. That was false. Oopsie. Oopsie doopsies. Anyway, e to the TA is actually equal to P, the e to the diagonal matrix, which works out to this, as this calculation above shows. And so here's P e to the diagonal times P inverse as it happens. And so, oh goodness gracious! So this was definitely take home. I'm sorry, guys. My bad. Let's end the suffering here. You guys, you don't have to understand these details for studying for your test. I am so sorry. We go on. Now, what follows, these are good problems for sure. Problem 8. You got this as your basis, right? Find the coordinates of AB. So I multiply by the inverse to the basis matrix. Voila, simple as. Problem 9. This is a given orthonormal basis, actually. I ask you to show that it's orthonormal, which means that you got to check these 6 dot products. As you can see, 0, 0, 0, 1, 1, 1. Those are what you need for it to be orthonormal. All right, perpendicular, all length 1. And as such, we can calculate the coordinates. Check this out, you. The coordinates, we just calculate the dot product of the vector with the orthonormal basis. That selects the first component, the second component, the third component, just like x hat, y hat, z hat, or if you like I, j, and k does in calculus 3, right? The dot product with I gives you the first component, the dot product with j gives you the second component, the dot product with z, with the k vector, right, gives you the third component. So same thing with an orthonormal basis, u1, u2, u3. This is the formula that we can calculate coordinate vector from. Notice we don't have to actually calculate the inverse of the basis matrix in this case. So like orthonormal basis, very nice. You need to know about this, right? Because if you have an orthonormal basis and I ask you to calculate coordinates and you're trying to like work out the inverse of the basis matrix, well, you're doing it wrong, right? It's just dot products, simple as. Now here, I just adjoined a 0 into the previous basis, right? I just slapped a 0. So this is still orthonormal. So when I calculate the projection of the point 1, 1, 1, 1 onto the subspace W, I simply just take the dot product with the basis multiplied by the basis. This forms the projection as we talked about. And lo and behold, there is your closest point as it happens. Can't draw the picture, but I can do the math. All right, now next up here, problem 11, we got, this is kind of like an earlier problem, but we got 2 vectors, find the orthonormal basis for the perp. So to find the perp, we find the null space of this, all right? And this one, notice that the null space of 2 matrices, which are row equivalent, is the same. So I just did a row operation. This, and like I did like row 1 minus row 2, I think, to get to here. And then so if x is in the perp, that means that it has to satisfy these equations in view of that matrix, right? X1 is x3 plus x4, and x2 is minus x3 plus x4 from the second row. Put it into your generic x, factor out the parameters, there's your basis for the perp, right? But that's not orthonormal, so we have to Gram-Schmidt that thing. So V1 is at the, V1 prime, V2, we subtract off the piece which is in the V1 direction. And that ends up giving me this vector. Factor out a third is a smart move, because you want to normalize stuff without fractions if you can. It's much easier to normalize this vector than the one with thirds in it. See, because 1 squared plus 1 squared is 2 squared plus 2 squared is, so 2 plus 4 plus 9, 6 plus 9, so I get 15. So I just divide by the square root of 15 to normalize that vector. And this one, of course, I just divide by the square root of 3. And there you go, that's your orthonormal basis for the perp. Simple as that. All right. Obviously, if you don't understand the null space basis calculation, you need to pin that down already. This will not stop coming back up. You need to figure that out if you haven't figured it out already. I think pretty much everyone knows, but there's probably somebody who's still shaky on it. Like, pin that down. The null space basis calculation. This thing I'm doing back here, where I'm writing x, is in the null space, means that it has to satisfy the thing that corresponds to this being equal to 0, and then I'm plugging in the pivot variables in terms of the non-pivotal variables, and that gives me a way to write the basis. All right, let's see here. So problem 12, we've got this basis here, which is, I think, orthonormal. Yes, it is orthonormal basis. And so I defined this mapping in terms of that orthonormal basis. All right. And so first of all, I was asked to calculate the matrix with respect to the basis, so I just do that. The thing is, if I feed it U1, the formula says it spits out 6U1. If I feed it U2, the formula says it spits out 4U2. If I feed it U3, the formula says it spits out 12U3, which gives me this diagonal matrix. Yay! So T gamma gamma is 6, 4, 12 on the diagonal. Now, to find the standard matrix, we can use the change of coordinates formula that we worked out. Remember, T gamma gamma is gamma inverse standard matrix times gamma. But because gamma is orthonormal, gamma inverse is the transpose. So I solve for the standard matrix like so, and then I just have to multiply by the basis matrix and its transpose. And after a little bit of arithmetic, we find that the standard matrix was this. All right? Is this a possible test question? Yes, it is. But, this would be a challenging one, obviously, because the arithmetic is a little bit fussy, right? And so I would definitely recommend that you have a calculator for this test because that could happen. All right. Oh, and I did check this. I actually fed this to the eigenvector website, and it reproduced eigenvalues 6, 4, and 12 like it should. Problem 13 was kind of a maybe a new kind of problem, but it's simple enough. So basically, I gave you two 2x2 matrices, and I built the big 4x4 matrix by their direct sum, right? And so one of these or the other of these we've seen in a previous surprise attack mission. But anyway, so the eigenvalues of this are this and that, which gives me this eigenvalue and that eigenvector, rather. The eigenvalues of this one actually are 3 and 7, so they both have eigenvalue 3. And so I found these, two-dimensional eigenvectors. Then, I took a break from this to say, what's the solution to the differential equation? Well, eigensolution using the eigenvectors I just found is just that. So that's, be ready for that problem. That's not a bad. You can solve differential equations if you can find eigenvectors, right? Not a big deal. There it is, general solution, e to the eigenvector plus c2, e to the second eigenvector. If the differential equation is order n, you should expect that there are n constants appearing in the general solution. This is second order, so it has 2 constants, all right? All right, anyway, I hope I've done enough of those that you understand how to do these. I mean, I know this is in a differential equations class, but that is an application that we've looked at in some depth, so it could be on the test. Now, the 4x4 matrix, this is just I haven't explained this, but it's true. What you can do is just adjoin zeros to what we've already done, and that'll work. And I show that it works down here and over here. See, if we just add zeros, we multiply, we get that, which is that, and that, and that. So as you can see, just adding zeros to our previous basis gives us an eigenbasis with eigenvalues -1, 3, 3, and 7 for A, like so. And that would diagonalize A like that, which is what I wanted. And then I asked you to show beta is also an eigenbasis for A squared. So I calculated A squared. And the way we square a block diagonal matrix is by squaring the blocks, as you can see. So we squared the blocks. I got this and that, which gave me this lovely 4x4 matrix. And when I multiply that 4x4 matrix on the eigenvectors, I get that they're eigenvectors. But now the eigenvalues are not what they were. They're the square. So we go from -1 to 1. We go from 3 to 9, 3 to 9, and finally 7 to 49. So that's kind of neat, I think. Problem 14 is a nice problem. We took the transpose of the Jordan 3 block, which gave us this. Now you guys, I told you can have a page of notes. You should definitely have what the Jordan 3 block is on your notes, so you know what it is in case you forgot, right? And so there's that. And then I just multiplied by the standard basis and tilt my head and squint and look at what it is. I got these equations, which means that, well, these are the chain equations. E3 is an eigenvector, E2 is a generalized eigenvector of order 2, and then E1 is over that still a generalized eigenvector of order 3. In fact, this gives us a 3 chain with eigenvalue 7. All right, that's what happened there. Now this one, problem 15, I want to clarify. I said something about not having complex I forget what I told you guys exactly, but I'd like to have this as a possible test question. All right, I don't want to make the more complicated, repeated complex eigenvector, or like even a 3x3 complex eigenvector, but it could be a 2x2 complex eigenvector, and its application to differential equations. I think this is worth you guys understanding. So please take a look at this and see how it works. It's not really that complicated. Basically, we find the eigenvalue, we find an eigenvector, in this case I1, and when you multiply e to the I3it times w, this gives us a complex solution, which when we write it out looks like this. If we take the real part, it's this. If we take the imaginary part, it's that. Those are separately real solutions, and so the general solution is this down here. Now this one is extra fun because it also, you said you wanted to go through the point x naught, y naught at time 0. So I have to fit the C1 and C2 to that data. And that's easy enough to do. It just gives me C2 as x naught and C1 as y naught, which gives me this over here as the equations for the integral curve to the vector field. So I think that's an interesting problem. It's something I'd like to at least possibly have on the test. Again, some of the earlier questions were not quite appropriate because they were, from a take-home. My apologies. Now this one here, also very much test-worthy. 2x2 system. This time repeated eigenvalue, and as you can see, we only get one eigenvector, so we go solve the chain equation, we get a generalized eigenvector of order 2 like that. So then we use the magic formula and piece together two kinds of solutions, one the eigensolution like so, and also the generalized eigensolution like so. So a linear combination of those two kinds gives us the general solution. So to review, if you have a system of two differential equations and two unknowns, there are three cases that could happen to you. You could have distinct eigenvalues, right, that are real, and in that case, you just have two eigenvectors, and you go back to like we had in part C of the other problem. If it's a complex eigenvalue, you just get one. All you got to do is find one complex eigenvector and do like I showed you in the last problem. We just take the real and the imaginary part of that one. The complex conjugate eigenvector doesn't even get used. All right. The other possibility is that you have a repeated root, and I wouldn't ask the silly diagonal case, so it would have to be this case. In which case, it's actually going to be a repeated root, and you're going to need to find a 2-chain and use the magic formula to put it together. But again, you can just copy down, these formulas with understanding onto your formula sheet and use them if you like. All right. I don't require you to derive the magic formula on the test. All right, that's what I'm trying to say. But I do want you to be able to construct the answer. All right. This one here is just, we talked about the matrix exponential, and if the matrix squares to 0, the matrix exponential's, well, easy to calculate. Here it is. So this one here is really just asking if you understood the magic formula and how the chain equations work, because if you sort through all this, you can see that the answer was B. B was the correct answer there. All right. Finally, problem 19 was a little bit vexing to some of you for at least a time, but I think some of you are on the right path, and I just got to it before you were done. But that's cool. So anyway, if you're given information about this, you can extrapolate from this statements about the columns of the standard matrix like so, and you can kind of the way these are given, like this tells me column 3. This information tells me column 3. And then this is like twice column 1 plus column 3 is equal to that. So I can piece out, I can figure out what column 1 is from looking at that, And once I know column 1 and column 3, then I can go back and figure out column 2 from the remaining piece of information. Of course, this is not invertible because this right here, this alone, if I just told you this and nothing else, this alone would kill the invertibility of T, because this right here is a non-zero vector which maps to 0, which means that the null space, well, it means the kernel of the map, or the null space of the standard matrix, is non-zero. And that means the nullity is non-zero, which means that it's not a one-to-one function. And it has to be one-to-one if it's going to be invertible. All right, with that said, let's take a look back down memory lane right quick. Here was SAM 6. All right, surprise attack mission 6. Remember what we did there? Found coordinate vector, great. And this one here, oh look, it's kind of that 4x4 block thing again, isn't it? I like that. I like that a lot. That's a way I can ask 4x4 questions which aren't actually that hard. So look for that. I'm fond of that trick, aren't I? Here you're supposed to find the standard matrix and then understand, is it one-to-one? Is it onto? So you look at it. It's got two 2 pivot columns, which means it's not rank 3. We would need rank 3 for this to be onto because it's mapping to R3. And if it doesn't cover all of R3, then it's not onto. So we have less, if you have less pivot columns than what it's mapping to, that means, in other words, another way to say it is if there's a 0 row in the reduced row echelon form of your matrix, then it's not onto. And if there is a non-pivot column in the reduced row echelon form of your standard matrix for the linear transformation, it's not one-to-one. So this one happens to be neither one-to-one nor onto. Problem 4, if you skipped it, I would encourage you to go back and look at that. That is an interesting problem, and it's got important mathematics in it about how we define angle and length using the dot product. And I think that's an important part of this course. I'll try to find some way to test on that. Now, mission 7, remember, was this thing I just had you work through my lecture. The main thing that you should have gotten from all this is that in the case we have complex eigenvectors, right? You can't, when you have a complex eigenvectors, excuse me. Complex eigenvectors, this is kind of the main point, is if we have a complex eigenvector, the matrix like 0, 1, minus 2, 2, it's not diagonalizable, but it can be put into so-called real Jordan form. So this is what we get if it's not diagonalizable, but it has a complex eigenvector. That means it can be put in. Basically, this is a rotation times a dilation as it happens. So anyway, I do want you to be able to find complex eigenvectors of 2 by 2 matrices, and it would be good if you understood what the real Jordan form was, at least for the 2 by 2 case. And I'm trying to think here. So it'd be good if you reviewed that lecture again, obviously. Yeah. All right. I'm just trying to really kind of real quick, go through these again. Mission 8. This one had a bunch of information, but the problems in the back are simple enough, right? Like show E1, E2, E3 is a 3-chain. So like on the quiz, I mixed it up. I transposed it, right? But same idea. Now notice that I forgot to ask about minimal polynomial and characteristic polynomial in the quiz. I'll try to. I mean, there should be something about minimal and characteristic polynomial on the test. Sorry, I didn't put it on the quiz. So it would be good to review these 2 problems about like what does it mean, minimal characteristic. So like the minimal polynomial is the polynomial of least degree that if you plug the matrix into it, you get 0. So I think these 2 examples are pretty helpful with that. But anyway, so there was that. This one here is very much like the one of the problems on the quiz where we had the repeated eigenvalue and we had to use the magic formula. This is like that. And I think this one fed into mission 10, right? This right here, no, not on the test. This is what I was talking about. This is pure evil, not on the test. Like if I asked you about, no, just not on the test. All right, not doing it. Wouldn't be prudent. All right, then 10, we cycle back to that. We work these out for that matrix in the previous one, and then we use the magic formula to write down the solution. All right, so there's another example of those. This calculation in problem 2 is a standard test question, like, diagonalize the matrix. So how do you diagonalize matrix, right? Find the eigenbasis, then you can similarity transform to a diagonal basis. You want to calculate the nth power of it. Well, you can easily calculate the nth power of the diagonal, and then you can similarity transform back to the matrix. So like that's, if you see a problem about finding the formula for like the nth power of a matrix, probably that is me asking you to diagonalize the matrix and think through that calculation. Here is a nice 3 by 3 problem that we can look at. We can find a 3-chain, explicitly calculate it. It's not too bad. And then we can use the magic formulas and construct, as I told you, third order equation, 3 constants, right? C1, C2, C3. So it would be good to study this example. That one's not too bad. That's a decent test question right there. Notice that when the matrix is triangular, calculating the characteristic polynomial is not a bad deal. I forgot to find the solution to this thing, but obviously you should look at this because you need to know the Gram-Schmidt algorithm. And this was a good mission. I'm sorry I don't have the solution to look at with you here, but you know, I'm particularly proud of this one right here. Sorry. Let's see here. Oh, in terms of a QR example, I think this one's better than the one that was on the quiz. Like this is a nice QR decomposition example, right? Because it's like, you know, the orthonormalization's pretty quick, and then we can find the Q and the R. It's not this is a decent test question. Something like this is a decent test question. It's not too janky. I think I talked about that a little bit. This one we kind of had one just like this on the quiz, right? I do, if you are still wondering about what I was talking about with eigencoordinates, I went into some extra detail over here to try to explain, like, if we change to the eigencoordinates, I explicitly do it here. You know, this is x and y in terms of the eigencoordinates, and if I substitute those into the formula, it simplifies down like that, which is pretty cool. And I proved down here that when I write that, that's the same as writing q of xy. So like q of xy is also the same as x bar, v1 bar, y bar, v2 bar. Like these are two different ways of writing the same point. So q of xy is this, but it's most naturally that. And generally speaking, it's this anyway. All right. So I gotta go eat supper. I gotta wrap this up. You know, on ChatGPT left me down here. This was supposed to have eigenvalues 6, 7, and 67, and it did not. ChatGPT's failure. It's a failure. Anyway, I'm sorry about that. I'm not sorry. And then this one, I think I more or less told you guys how to do problem 1 in class, so I hope that went okay. I'm very fond of this reverse engineering of examples. It's very cool. But anyway, I gotta go. Sorry, I can't spend longer on this video. And this, you know, this I think doesn't make a bad test question. To make it a test question, rather than doing 3, maybe I just do 2 vectors. You know, Gram-Schmidt 2 vectors in inner product space like this, something like that. I ended up getting this, which is kind of, it's a little bit different than our other result in the notes, right? And that makes sense because this is closest to the exponential with respect to the notion of distance being judged by the integral from 0 to 1 as opposed to -1 to 1. So I kind of not surprised it's a little bit different. Anyway, I think somebody else had these same numbers. I think I checked that. Oh no, I couldn't check that. If I'm wrong here, it's possible that I could be wrong here. I don't know if I had anybody check against me. But anyway, I hope that helps you guys. I will try not to make the test too long, and but you know, it should obviously have eigenvector questions that are explicit. There should be some symbolic eigenvector questions where it's just about, do you understand the definition and can you do some basic matrix algebra at a symbolic level? That should be part of the test. There was some of that in Surprise Attack Mission 7. I did some things like, you know, about the eigenvector for A. What does it say about it being an eigenvector for A squared? Thing like that. And then, of course, don't forget about the stuff we did right after the test, like the coordinate map, the, you know, is it 1-to-1, is it onto, find the standard matrix, you know, the coordinate change for both the vector and for the, you know, the non-standard matrix for a linear transformation, something we covered, it's important. What's a rotation? What's an orthogonal transformation? How do you find the angle between 2 vectors in, say, R5 or something? We should be able to do that as well. Even though I don't think we had a question, but we talked about that earlier in the course. And then, of course, like I was saying, you know, be expecting eigenvector questions, obviously, and I would expect that there, you know, obviously the perp calculation, like how do you find the perpendicular to a space? How do you find an orthonormal basis? How do you find the closest point to a you know, to some subspace? And then, and of course, the least squares problem, we've talked about that as well. So I said I didn't want to make the test too long, so I'll figure something out. But anyway, have a good weekend, you guys. Just do your best. That's what I want you to do. So anyway, thanks, guys.